Before we went through the definitions of group velocity and phase velocity, we watched this video where we have an envelope with some carrier frequency underneath, and we watch the envelope propagating along at the group velocity while the ripples underneath are moving at the phase velocity. Now what I want to do is consider what happens if instead of having a single frequency under the envelope, we have multiple frequencies. So to flesh out this example, we're going to have three pulses with three different frequencies. Each of these pulses has the same envelope, and each of them are narrowband. And by narrowband, what I mean here is that the period of the carrier underneath is much, much smaller than the width of the wave, so that the length of the wave is much bigger than the oscillations underneath. There are many oscillations underneath the envelope, in other words. So these are what we call narrowband pulses. When we add them together, we get something where the envelope has the same shape and width, although it's been scaled. The height is now 3 times bigger because we're assuming here each of these pulses has the same height. If we give them each unit height, then the height here of this envelope must be 3 times bigger. Underneath we have a bit of a mess because we have beating between these three different frequencies. So it looks pretty messy, but there's still an envelope and there's still frequencies underneath this envelope. What's going to happen when you put it into the dispersive medium? The wave propagates and the three frequencies separate into their respective groups because each of those pulses has a different phase and group velocity. Each of them is narrowband. They're narrowband because the pulse is long compared to the period of the carrier underneath. And so because everything is linear, the three pulses just travel along and separate away from each other, and we see that dispersion separates the frequencies of these different pulses. Now, it's important here that linearity means that these things don't interact with each other, they just separate. So the pulses don't affect each other, they propagate just as they would have propagated without the other pulses present. This is also the same effect, by the way, that turns white light into a rainbow when you shine white light into a prism. So white light travelling in glass, the different colours of glass, red, green, blue, have different refractive indices. The different refractive index means that each of those colours, those different frequencies, travel at different speeds in the glass, just like these frequencies here travelling at different speeds. In this case, we have three pulses of different frequency separating in time, or in space. In the case of white light exiting a prism, the different refractive indices means that Snell's law is different for each of the colours of light, for each of the different frequencies, and so we get an angular separation of the colours of light, but it's dispersion nonetheless. And rather than separating pulses in time or space, Snell's law separates the colours of light in angle.